So without further ado, let's get started. So I'm here to talk about Kubernetes, and Kubernetes is this project which allows you. It's kind of like revolutionize the DevOps world or deployment world in general. And Google apparently has been using it for a while. We'll look at what Kubernetes is, and I'm viewing it from a developer standpoint, right? Not from an operations standpoint, but from a developer standpoint, what Kubernetes is and how it can help us, and how, as a developer, I can interact with Kubernetes, not just writing YAML files and things like that, but writing with code and controlling how it works and all that, right? So, but first we need to talk about VMs and containers. Actually, and a lot of people have this confusion. You guys use VMs for sure, right? Yes? No? Yes. Okay. So, what VM software do you use? We'll keep it interactive. So, what do you use? A VMware? VirtualBox. Okay. Anything else? Anybody KVM? Okay. So both VMs and containers, basically the goal of both of them is like isolation. Right? So when you're running an application, you want to make sure that the application doesn't affect other things at all. So you are basically building a wall or a boundary around it, so that you have a big resource and you're able to partition it, so that you can give, because I mean many servers that you get 128 GB of RAM, or like 256 GB of RAM, or even 64 GB of RAM. But most of the applications we write, they require far less, maybe 1 GB, 2 GB. Maybe if you are running Elasticsearch or something like that, it may probably take all the. But most of our applications require smaller bits of RAM. And if you are able to isolate that process, you will be able to pack more things in a single base application. And then we can do that. Maybe we can turn off this fan alone. So that's basically the VM. So the virtual machine, the way it works is that you have the machine, which is basically the violet box here. You have the kernel. It could be Linux, it could be Windows, whether it's the base operating system layer of the kernel. And then you have the hypervisor. Right? Hypervisor is basically like VirtualBox, what you have, or Zen, or whatever it is. That is the hypervisor. And what the hypervisor does is that it emulates a brand new machine. Right? It basically says, okay, now you have a CPU and your memory and your network card and your SCSI controller or SATA controller or whatever. And then on top of that, you can install another operating system. And then the whole thing starts from there. Right? That's a VM. So that means that, say for example, if you are writing a Node.js app and you deploy it on a VM, so before the Node.js app can talk to the outside world, it basically has to go through your app, goes through the Node.js libraries, which is V8, goes through libuv, talks to the kernel, talks to the hypervisor, talks to the underlying kernel, and then goes to the outside. It's a lot of waste. You don't need, if it's just an application, you don't need that. Right? Instead, the containers take a different approach. All the processes which are running on containers, they share the same kernel. Right? If you are running on Linux, all the containers will also share the same Linux kernel. So that means that you cannot run a Windows container on a Linux machine, or a Linux container on a Windows machine, or as I'm going to do now, I cannot run a Linux container on a Mac. Right? So if I have to do that, I have to start another maybe VirtualBox which has Linux on it, and then share the kernel with the rest of my containers. So that is the restriction with the container. But container, as you can see, is a lot more lightweight. So you don't have as many parts that it needs to take through. And starting up containers is significantly simpler than starting off VMs. Given the fact that your container only needs to launch your application code and does not need to launch an entire Unix system, or it doesn't need to launch an entire operating system bootstrap process. So starting containers is significantly faster and takes only the resources that your application needs and does not need any of the other resources that your VM needs. So your containers are often more efficient than VMs. Okay? So, but it's kind of a true these statement. The reason I'm saying true these statement is that there's a lot of work going on into also making VMs lean, but that's still not in the real world yet, or say in the mass sort of adoption yet, right? So far, containers are a better ways to deploy applications than VMs, essentially. Right? But containers are not a new thing, actually. Containers have been around for a long time. So we'll have a quick look at the history when it started. So first, for the initial this thing of what a container is like it started off in Unix, V7 or System 7 or thing. And this was done in 1979, 2 years before even I was born. I'm sure it was before many of you were born and after some of you were born. So let's not get into that. But the thing is that so Unix is the first system which basically said, okay, so I am heavily biased towards Unix, so and Linux-based operating systems. Because unlike Windows, everything is in a file system on this thing. So there is no registry, there is no this thing. Everything in Unix, right from your device to the process library to anything that is kept in memory, everything is addressable as a file actually. So in Unix, it's so powerful that if you change the root directory to some other directory, essentially you are in a new machine actually, which is not the same on Windows machine, because you need to then also emulate your registry and the rest of those things as well. But in Unix, essentially changing the root basically gave you a level of process isolation that it was not possible otherwise. So if you start off a process with a ch root inside it, or they call it chroot, so then it will basically say that, oh, you cannot access any of the other files in your system, and hence it's secure. So it's very difficult to break out of ch root. So the process that's launched within a ch root, it is very difficult for it to break out and see any of the other files around. And BSD basically gets it in 1982. So if you know any of the history of Unix, it's they had two distributions. One was the Unix as a commercial core, and the other one was BSD, which is done by Berkeley guys. And what's running on my machine, which is Mac, is essentially BSD. Right? So they basically forked BSD, and Mac is essentially Unix at this point. And FreeBSD was the open source version of BSD, and they added support for Jails in 2000. And Jails was like a more mature system than chroot, and it's not just gives you file system isolation, but it also gave network isolation. It also gave like CPU memory isolation and things like that. So, for example, if you had a quad core machine, you could say, oh, you get only 2 cores for this particular jail. Or if you have, at that point in time, if you had 64 megs of RAM, you say only 8 megs to this jail and things like that. So, and these are all containers. That means that they still share the same kernel. So you still, for that process which is running under the isolation, it still had to be compiled for the FreeBSD kernel for it to run. Actually. And then Linux vServer gets added, and it ports jails to Linux. As you see, Linux and Unix and BSD have all been sharing this thing. So in 2002, I think it's one of the first proper implementations of containers on Linux came out, and it was Linux vServer. And until 2006, they had been shipping patches, after which the project was abandoned, actually. And around 2006, OpenVZ got released. Now, VZ Systems was actually marketed as commercial software by a company called SW Soft, and they had been doing it since 2000, actually. But in 2006, OpenVZ came out, and OpenVZ was probably a big competitor to the VMs, actually. They said OpenVZ actually was promoting themselves as VM rather than as containers, but essentially their limitation was that you had to share the kernel, and they basically didn't talk about in terms of containers at that point in time, and VMs were basically the hot topic. But OpenVZ was essentially a container-based technology, or similar to what we think of containers. And finally, in 2007, or rather 2006, actually, Google also started working on proper C groups, and they call it process containers, actually. And they abandoned, the interesting part is, Google abandoned the name containers because container is used in the kernel code base in many cases. So they actually abandoned the thing called containers, and they renamed it to C groups, which is control groups, actually. And this happened in 2007, actually, right? And finally, the full-fledged sort of like using namespaces and control groups and all that, LXC is released. So LXC is arguably the first, I would say, proper container system, like similar to what Docker is right now, actually. So I mean, Docker has all the infrastructure for images and all that, but essentially the runtime infrastructure for where you basically are able to attach a file system, process and memory restrictions, and also do like other restrictions in terms of how much priority they get and so on and so forth. I think LXC was the most mature thing at that point. And Cloud Foundry basically releases Warden in 2011. So it took 3 years, and Warden was very similar to Docker as it exists, or as it existed in 2013 or what. So there were 2 years before that, and Google then basically after they did all the work on C groups, they actually started working on Borg. So 2007 is basically when they started the Borg effort actually in Google, which basically set the foundations for Kubernetes as we see today. And Google actually allowed application developers to quickly turn their applications into containers by having this project called LMCT5, or let me contain that for you sort of thing, actually, right? So you give me an application and they'll turn it into a container sort of thing, right? And this started in 2013. And we haven't even come to the slide where it has Docker. And Docker also releases in 2013, right? So many people that they talk about containers, they say Docker, right? But there's been a huge history towards the build-up of Docker and what made Docker inevitable. And what really set Docker apart from the rest of the competition is essentially their execution. Because I had been following, so in 2013 I had been following Docker releases very closely, and they used to have a release every 2 weeks, actually, which was crazy. I mean, they used to have a minor release every 2 weeks, and they used to keep adding features. And what also enabled them to move this fast as compared to other things were also that they were building this on top of Go, actually. So Docker was probably the first proper container application built on top of Go. Because even LMCT5 was built with C++ actually. And then Docker decided to basically buck the trend and say, hey, anyway, these are basically C groups and namespaces and all those kind of things, which are, either system calls or directly manipulating file systems and like running commands and all that. So I can as well do that with Go, and that actually gave them a huge productivity boost, and they were able to ship features and acquire a community far faster than any of the other things. And then the ecosystem after that basically exploded because remember Google started LMCT5, they abandoned LMCT5, and whatever ideas that they had in LMCT5, they basically put it into libcontainer, and Docker uses a libcontainer actually. So essentially whatever code that Google wrote or ideas which it had for LMCT5, basically they joined the open source effort and it came to Docker. Now, Docker has 2 parts. One is open source Docker that all developers love, and the enterprise Docker, which developers don't like very much actually. Right? The company Docker is not the same as the open source product Docker, right? And so because of which, I would also say it's kind of like a sneaky move. The founder of Docker, the CTO of Docker basically, when he was leaving Docker, the company, he basically had orchestrated a series of projects which basically took away all the plumbing from Docker. Essentially, whatever was branded as Docker entity. So they had this open container initiative which made sure that the Docker standard is basically an open standard, that it's not steered by the company anymore, and it's like an open source open body. They then took libcontainer and made sure that whatever is the core bits of libcontainer was basically put in that. And then they took all the runc based things, which is basically any container runtime specification, and they all put it in the runc project and all. And slowly, Docker essentially became like this enterprise shell for a core of open source technologies, which Docker didn't own anymore, actually. So, and that's partly the reasons why Docker, the company, is in trouble right now. So, yeah, and then, yeah, as I said, the ecosystem completely explodes. Kubernetes is released. Kubernetes is about 2 years old since 1.0, and Kubernetes has essentially, accelerated the container adoption in the mainstream, actually. And apart from that, there is also Nomad from HashiCorp. HashiCorp has been pushing a lot of good tools around the DevOps community. They built Terraform, they built Packer, they built the Vault and all that. And now Nomad is also one of their container orchestration tools. And then Docker itself has another product called Swarm, and Apache guys, they have an Apache Mesos actually has an implementation for container runtime as well, runtime orchestration. Okay, any questions so far? Please feel to interrupt me. I see a lot of glassy eyes because understanding this is kind of important as we go forward. Any questions? Anything at all? I mean, how do you, anybody deploying any applications on VMs, how do you do the deployment? Very silent. So how do you generally do your deployments actually? Do you use MSI? I mean, I know you are a big Windows shop here. Do you use like MSI installers? Do you use install shield, install script? Or does anybody know? Okay, so I'll move on. We'll get to the. So here I'm talking about. So forget about the YAML bit. So usually, when people think about Kubernetes, all they think of is like this deployment manifest, like huge balls of YAML files that you have to deal with. Actually, that's not how the Kubernetes team intended Kubernetes to be used. But that is how Kubernetes is used now, actually. So that's the unfortunate situation is that people, I mean, they had this really nice command line tool called kubectl, so kube controller, which they were primarily used for testing and things like that. But that kind of became the standard of how to interact with Kubernetes. So we'll walk through some of the like deployment manifest and like some of the aspects of it, and then we will, in our live demo, we'll try to see how things work. So here we are basically dealing with an application called Prometheus, and Prometheus is a very interesting application because it monitors. It does a pull-based monitoring. So for example, in your application, you would publish metrics. So you would say some method or some measure that you care about is so much. It could be a counter that you increase, or it could be a gauge that you say, oh, I'm processing 200 messages per minute now, or I am processing, oh, I have this particular request has been called 20 times and things like that, right? So you basically have histograms or counters or gauges. Now after you have these, you will basically publish them with tags. You say, oh, these are total number of HTTP requests, but and then you would basically say some key value sort of thing, actually. Now what Prometheus does is that it scrapes all that content, and then it will give you a querying tool that you can construct like a full-blown dashboard and other things on that. So this is usually people install Prometheus, multiple Prometheuses in an enterprise setting or in a cloud-based setting where they're monitoring all these things. Now this is one such thing. So here when you are deploying it, you basically give the metadata saying what it is, where you are going to install. So this is the name of the application that we're installing, some name, and then some namespace which is basically has a logical grouping of where such software is running, and some labels to identify them. So it says that this is a core component and it has an app : Prometheus. Both labels and values are strings. From Kubernetes itself doesn't care about it, but you can build tools which can then care about it on top of that. Okay, and then finally you say what to run, and this is basically saying that, oh, I want an image called prom/Prometheus, which is basically a Docker image that you're running. You say these are the arguments that you need to pass for it to run, actually, and that's about it. And finally, you also have to say, I want 500 milliseconds of CPU, and I want 500 megabytes of memory, right? And if you see the 500 megabytes of memory, this is all the memory chunk that you want, actually. So it kind of matches, saying that when you start the application, you should have an idea of how much CPU and memory is going to consume at some point in time. Otherwise, you can always measure and then set some value. And once you provide these three things and you run this, you basically tell Kubernetes, go ahead and install that. Kubernetes will basically is running over a farm of servers, right? It's going to say run on say 500 VMs or 500 physical machines or nodes that it's controlling. It will basically say, okay, which is the node which has this limits for me, right? And we'll go ahead and put it in there. So Kubernetes does automatic bin packing for you. Since it does automatic bin packing, it will be able to do a much better job than you are. And if you feel you can do a better job than Kubernetes scheduler, you can write your own scheduler, and you can basically also, like how you have all these things, you can say scheduler, my scheduler, and it will basically ask your code saying that, oh, these are the nodes, these are the requests I've got, you tell me which node to put it in, I put it in there, right? So you can also do that. So let's let's quickly talk about, I've been talking about Kubernetes, so, eh, no talk is, complete without a block diagram of what this has. So, usually when you think of Kubernetes deployments, you don't think of one node or two nodes, right? So usually you have at least 20 servers, 10 to 20 servers for it to become meaningful. And Google and or even Amazon in EKS right now, they claim to be running these Kubernetes controllers on top of like thousands of nodes, actually, thousands or hundreds of thousands of nodes, actually. So at the core of all these things is there's this controller plane. So almost like most of the cloud software, they have sort of like a controller plane which basically does a configuration management and all those kind of things. And then they have the workers, which they call nodes, actually. Now for controllers, all the database that's there, so all of the Kubernetes core components are actually in this color blue. For other things, I put other colors, but all the blue colors are basically the Kubernetes components. Everything else is like things that are associated with Kubernetes. So when you basically say this is the YAML file that you have to deploy, all this data needs to get stored in a database somewhere, right? Because you are telling Kubernetes, go run this. So Kubernetes needs to take care of what needs to run, where it needs to run, and what is the status at each point in time. And regardless of which server you ask, it should basically say the same answer, right? To which case you need a database essentially, because you can't rely on memory to basically fill it. So to that effect, they have a database called etcd. Now, etcd is a very interesting database because it provides a distributed fault tolerance. That means that you can start etcd on 5 nodes, and as long as there are 3 nodes available at any point in time, you can guarantee that the answers that you get will always be consistent, and the writes you do will always be consistent. So it provides like a distributed fault tolerant store, and it makes sure that this is all the data that's stored via Kubernetes is always safe, always available, and always consistent. Actually, now it's not the most performant database in the world, but it suits for this sort of like configuration. Storing critical pieces of information that needs to be kept. But it performs reasonably well, better than most of the SQL databases, but not as good as Redis or any of the other key value stores. So it's somewhere in between, actually. So on top of that, whenever we talk to Kubernetes, we work with the API server. So API server provides a REST API to all of the Kubernetes components. So that means that even when we are going to write our application code which is going to talk to Kubernetes, we are actually going to use the API server to talk to Kubernetes. And then there's this scheduler which basically says, okay, where should I schedule a job? Once you've created a job like that, like how we say a deployment, it now says, okay, which node I should put this in, right? Depending on the selectors you have and things like that. That's the scheduler. And you have things like the controller manager, right? So in a sense, right now we asked it to do a deployment. In case you don't see it here, but this on top of this, there's this word called deployment. Probably you can't read it. So it is a kind of a deployment, right? In a sense, this is a type of an object. So there is a controller which basically says, oh, I want to look at all the deployments, and once I get a deployment object like this, I should do something. So those are called controllers. And the controller manager basically has a whole bunch of these controllers to do with stateful set, persistent volume, config maps. Like there are several primitives in Kubernetes. It deals with all of that stuff actually. And so this is all in the controller. So now if you see in the controller, you don't run any of the workloads on the controller, right? So workloads are basically run on the workers. So this basically provides, like if you use Jenkins, you have Jenkins the software and then you have Jenkins the workers, right? So this is basically the controller which basically says, okay, and you can have more than one of this, right? For example, you can have three API servers, each one availability zone or in disaster recovery, and then put it behind a load balancer, and you can even round the robin between that. So it's perfectly safe to do that as long as etcd is safe actually. And after which you can have any number of these nodes. Like I said, Kubernetes scales to really, really large number of nodes, even 10,000 nodes and so on. And on top of that, it uses this container runtime interface actually. Now, Kubernetes is not tied to Docker, so you can replace Docker with any of CRI any CRI compatible, what is it? This thing. So you have runc, which is by Docker. You have CRIO, which is there. You have Rocket. You have many of the other things which, or even like things that are currently being. When you could write your own as long as you follow the CRI spec, you're good actually. And writing container engines is hard, but it's not that impossible. Now, right now, people have started writing simple container engines as a part of their like talks and things like that. So it's become nice. And kubelet is basically a server that runs on the node. This runs as a daemon, and what it does is that it actually takes all the like for example, when scheduler says I need to run this, kubelet basically takes that specification that scheduler gives and then talks to CRI, and then CRI makes it happen. Right? Whatever CRI compatible container runtime is, that makes it happen. And kube proxy is like a special service where so the way in which Kubernetes works is that the networking model is that you basically have whenever we create this pod, right? So this is called a deployment, and this deployment creates a pod. Now this pod actually gets its own IP address. Every pod basically gets its own IP address. So it's crazy, right? So imagine you are basically starting a Node.js app. Your Node.js app will get its own IP address. And if you have 5 copies of those Node.js apps running, which is normal, you will actually have 5 different IPs, actually. So you need something to load balance across all these things, because as you scale, you need to do that. So you write services. And imagine if you have like 10 different nodes, and you start 5 of these copies of your application, each may get started on different nodes, right? But when the service comes in, it basically needs to talk to any of these kind of things. So that's what kube proxy does. So kube proxy proxies requests. Regardless of which node it hits, it knows which path it needs to take to the next application. And this is done with IP tables rules right now, and there are better alternatives coming out. But yeah, it's quite interesting once you start digging into Kubernetes, and if you already know IP tables and how to write rules and how to change them and all that, it's very interesting how kube proxy implements those rules. And on top of that, these are just Kubernetes components. But for Kubernetes components to be successful, like I said, the networking is a very, very important aspect because the networking model which Kubernetes has is very unique in a sense. Rather than saying everything is restricted to a host and then you do this, they did not want any of the Kubernetes components to be in the hot path when a request comes. Like for example, you have an application and that's exploding, right? And you're just getting a lot of traffic. The last thing you want is one of the Kubernetes core components acting as a bottleneck for your application. So what they did is this whole flat pod IP thing is basically because of that, which is that now you let the Linux internet networking layer take care of routing traffic, right? Or you let Amazon VPC or something like that, some dedicated networking layer taking care of traffic without any of the Kubernetes components being a bottleneck. And that's what CNI does actually. CNI stands for Container Networking Interface. So you'll have a lot of C, some letter and I, container something interface, because the community is standardizing about many of these interfaces right now. So one of the other things for storage is like container storage interface actually, right? So any of these horizontal aspects about containers, they are all getting standardized. And so CNI is one such standard, and it kind of is an orthogonal concern of Kubernetes, right? We say, Kubernetes only cares about, I want to have these pods, and it basically says that every pod should have its own IP address. I don't care how you do it. And so CNI provides a way of doing that, and it has various plugins it can have, and that itself can run on top of Kubernetes as a pod actually. And then finally you have kubedns or CodeDNS, because in addition to Kubernetes being a resource manager and a resource scheduler, it can also act as a service mesh. So in case, how many of you are familiar with microservice architectures? Have you heard the term microservices and how to do this? I see 1 hand, 2, 3. Okay. So service meshes are basically ways in which you can discover applications. Say for example, now when you start a service, you basically say, I want to start it on this port and whatever, right? So as long as you have 10, 20 services, it's fine. What if you have thousands of services like that, right? You cannot obviously keep remembering which port this is starting, which this thing is starting, and you can't basically do, right, say this, is this microservice up or down, and do all those kind of things. So service mesh basically takes care of all this. Service mesh is more of an idea than a technology. So the idea of service mesh is that once a particular service is up, it should be in known locations, and you shouldn't worry about too much configuration and things like that. So for example, if you have your DB for your application, you should always be able to access it with DB as the host name, right? And it's the job of a service mesh to make sure that whatever services that you depend on is available in a well-known name for you, and that's about it. And kubedns and core DNS actually do that. Earlier there was kubedns, now the Kubernetes community as such is moving towards core DNS, which is better architected than this thing, and it uses HCDS, its database store, and so on and so forth. And finally, you have all these HTTP services. Now I said every pod gets its own IP, and every service gets its own IP. But none of those IPs are externally accessible, right? They are all internal IPs. So to make it externally accessible, you need to expose them as HTTP endpoints and things like that. And that's where you have ingress. So ingress is a very fancy word for incoming, actually. Right? If you network engineers would know ingress and egress a lot, actually, but for normal developers, ingress and egress is not in our day-to-day vocabulary. But ingress is basically saying, okay, how does the traffic come in to the site, right? And you have, Nginx is probably the most widely used. I mean, you probably use IIS here to do that, or any of the application load balancers and things like that. And there's a whole bunch of products in the market which actually only focus on application delivery, right? Where they say, oh, they do patterns like short circuiting and things like that. So and all these pattern problems only occur when you are at scale, right? So if you are solving city scale or say country scale services, then all these problems come into picture, because a few servers may go down, right? And then you still need to recover from that, and your application shouldn't crash because of those kind of things, and so on and so forth. And there, these kind of back-end application delivery solutions actually become very important. So this is overall in terms of what Kubernetes is. So without further ado, we'll probably have a small demo if you guys are interested. Oops, it's really bad. Let me change the. Oh? No. I just need. I'll just change the appearance. So I actually have a Kubernetes cluster running locally, and it's called Minikube. What Minikube does is that it actually runs a virtual box on this thing and runs all the Kubernetes components that you have within this. So for example, now I can say kubectl get nodes. So this gives me all the nodes that are running, and right now it's already running Minikube. It's been running for the past 33 days. So the OS image is build root. That means that it's a very specialized image where only the basic things are there. And I have the kernel version 4.15.0, and this is the Docker version. So Docker 17.12 is installed actually, and this is a pretty old version of Docker, because Docker basically gave up all the semantic versioning, and they've gone to some really weird versioning, this thing which is causing people a lot of grief. But anyway, it's almost a year old Docker that I'm running. So if you see here, whatever I talked about, right? etcd, API server, controller manager, DNS, proxy, scheduler, everything is basically running as as Kubernetes pods themselves actually, right, or Kubernetes workloads themselves. And this is a little weird. Usually people don't do it because it creates this weird self-referential problem, because you need Kubernetes to, Kubernetes needs all these components to run, but when the kubelet starts, it can start all these things because of a hack which says you can run static pods and things like that. Usually it is not the preferred approach, but since it's running on the local machine and there's only one node, it's actually pretty easy to do it this way. And once it's done, so I can, it's a fully functional Kubernetes this thing. So what I'm going to do is I'm going to run an Nginx application and basically try to access it from the outside world. Sorry. I probably should expose it a little later, but so this basically creates a deployment called Nginx, where I'm able to run Nginx. So if I say kubectl get pods, it's going to show me that I'm running Nginx over here. This is the Nginx, the thing it got created. So this is also going to say that this is only 16 seconds old and this is the Nginx thing that's running. Now, if I have to access this, it's going to be hard, because now if I say get pods wide and I try to access this IP address, it won't be possible. It won't be possible for me to access this IP address, because this IP address is something that's local to the VM, right? Or local to the Minikube instance. I cannot access this thing from the outside world. So if I have to do that, then I have to expose it as a service outside. To do that, I have to say expose Nginx 80. So what this will do is so I can say, hold on one second. Let me just quickly look at the documentation, because I need to provide the IP, actually, port IP. So this basically exposes this thing. Now what it does is it creates a service called Nginx. So let me get that. Kubectl get svc. Now it says that I have this Nginx service, but even here it creates this cluster IP, right? So when it gives the cluster IP, it doesn't give this thing. So I need to probably do this with a host port actually. So if I can set the type of this, I can basically say because I know this thing is running on right 192.168.9900, and I would be able to access 192.168.9900, but I can't access this port, which is 10.107.218.21. Even this is a separate IP address range reserved only for services, so even this I cannot access. So let me try to expose it as a host port. So let me delete this one particular thing and expose this again. Equals 80. Hide this so that you can see this. And sorry, node. Right now, if I give get service. Now, if you find here, it say that now it is accessible on port 31654 actually. So let me try to expose this, access this. So now it says, okay, now I'm able to access it and it's giving me the HTML output for this thing. So this is kind of like the hello world for Kubernetes, right? Everybody, I mean, so you are able to create a service, do all these things and do it. Now, what would be more interesting is if you are able to find out, if you can get to what sort of service is running, right? That will be pretty interesting. So if you look at service, I also have an other service called Reflector. So let me also delete this because it's also exposed on a cluster IP. Let me try to expose this on the node port. So it's running on port 3000. I know that because I wrote it. Um, Right. Now I have a Reflector service that's available. So let me list these services. Now Reflector is running on node port and it's running on 31741. Now if you look at kubectl get pods, so I have a bunch of Reflector instances running. So I have one deployment, but it's actually running 6 different copies of Reflector. And if you say wide, basically you would find that each one actually has a different IP address assigned to it. Now the Reflector is a very simple program. All it does is that it actually runs on Kubernetes and it tries to reflect on what IP address is there, which node it's running on, which namespace it is, and all those kind of things, and then return that as an output. So what we are going to do is basically access our service to find out that it's load balancing between these 5 different things. It's running on one node, but even the effect would pretty much be the same, even if it's running on a 5 node, 10 node, 100 node cluster, it will essentially be the same. So let's get to the service. 31741. Right now, you see, I'll also make this a little nicer so that. So if you see here, it comes from 15, 13, 9, 15 again, and if you see the pod IPs are changing. What Kubernetes is doing internally is that it's randomly picking one of these nodes, one of these pods is running, and just sending traffic to it actually. So that way you're able to access. Essentially, it's load balancing for your service. And immediately you can see if it is running on multiple nodes, how much easier it would be. Because earlier now you had to worry about how to write a front-end load balancer, write rules for it, and so on and so forth. With 2 commands, we were able to just expose this by pointing it to some deployment and say, oh, this deployment has 5 of these nodes, and so you do this, right? Now let's try to do one thing. So we have 6 of these reflectors. Let's try to change the deployment so that there are few of this, because we currently have no load. We'll try to reduce the number of these things. Right, so this is the reflector deployment that's there. And what I'm going to do here is, you have this replicas 5 here. That means that it has 5 replicas. I'm going to change this, and I'm going to say 3 is enough for me, actually. I'm going to save this. So now that this has been replicated, so now if you see kubectl get pods, you see here, a couple of them are terminating actually now. That's because you don't need that anymore because reflector is running. But your curl would just work fine. The moment you say these are being terminated, Kubernetes basically rewrites those networking layer rules so that it doesn't do that. So that means that Kubernetes components are never the bottleneck, right? All they do is like change the rules for your networking combination, but they never are in the hot path to accessing your service underneath, actually. So the next thing what we're going to do is what we promised. We are actually going to write. How many people have worked with Go here? Go programming language. Sorry.
When you change, right?
Yeah.
You change the application from 5 to 3.
Yeah.
So it automatically, you automatically restart the Kubernetes side or
So I did the edit actually. So if you see here, I edited the deployment. So it got the YAML file and it gave me here. So once I saved this file and quit this, so I would say 7 again, okay, and I exit, save it and exit. Automatically it finds that the service has changed, and when you do this, it will basically say container create.
So it automatically triggers the
Yeah, creation. Yeah. So what has happened is I'm talking to the API layer, basically getting the manifest file, saving the manifest, sending this back again to, because it writes to a temporary file. Once I save the temporary file, it sends it back to the API server. The API server basically reads this, sends it to the controller manager. Controller manager then talks to the scheduler, finds out which node I have to go to. In this case, there's only one node, and then it talks to the kubelet and says runs this. And then the kubelet then talks to the Docker container within, and then it starts running.
all this goes to synchronization. All the components goes to synchronization.
Yeah, so this is called, this pattern is called a state enforcement pattern. So you say what your state is going to be, and basically let whatever controller they are running to enforce the particular state. So, and that's usually a very good pattern to follow in for infrastructure components and things like that. So, because eventually it will get to a consistent state that you have declared. So now, okay, let me scale down this replication, or it can be there, it doesn't matter. So what I'm going to do is, I'm going to create a, so how many of you are aware of Go or written some Go? One hand. So one, okay, two. Anybody else? Yes, true. Okay. So Go is a programming language again created by Google, I mean, so essentially there's this age of C, C++, and then people got mad for a bit and started doing Java actually, and then Java slowly became mature and it started running on the server and all those kind of things. But people who were doing C, C++ still continue to do C, C++ actually, in a sense. For system components and things like that, they really didn't have better alternatives to actually build systems which scaled very well, because Java again had, there was a lot of iteration on garbage collection in this thing and so on and so forth. It was good for business applications, for but any of the system stuff, it was really bad actually, and it didn't scale very well. So the Go team basically started looking at it. They actually wanted a better programming language for writing the system components, and they basically said, okay, what if we wrote C now in today's day and age with the following this thing and all that? How would we reimagine a language like C actually? And they came up with this language called Go, and it's been around for the past 10 years actually. And for the biggest feature of Go for the past 10 years is that the core language has not changed actually. So it's still in Go 1, and whatever language features were supported 10 years back, it's still the same, right? There has been a lot of changes in the runtime, but whatever code that you had written like 10 years back, it would still compile actually. So that a period of stability has given Go a lot of advantages in the terms of the code base that it has accumulated actually. And a lot of system components in Google are basically shipped with Go. And if you see, Kubernetes is written in Go, Docker is written in Go. You take any of the newer infrastructure software like etcd and things like that, they are all written in Go actually, and that makes it very very suitable for this sort of work. And there is also another language by the Firefox community or Mozilla actually, and that's called Rust actually. And Rust and Go are kind of similar. Similar in a sense, they basically were born out of the same need that C++ and C are antiquated. They don't provide any memory safety and things like that. And they actually wanted a better language which provided memory safety without having to give up performance and all that. And that's how Go and Rust were formed. I personally like Go. Rust is also an amazing language. But yeah, it's the community around Go and the tooling and the libraries is all more mature in Go than in Rust actually. So let's create a project. So the goal is within 100 lines of code, we should be able to talk to the Kubernetes cluster and do something meaningful. Like for example, we created Nginx, we should be able to create another pod like Nginx and talk to it. Let's see if it's possible, right? So let's create a house. I use Visual Studio Code. Anybody using Visual Studio Code here? What is Nginx 1, 2? Right? Cool. So I think Visual Studio Code is like amazing. They have done a really good job. When it works really well. So, hold on one second. I don't know why it's taking so much time to load. It's also an Electron app, so sometimes Electron apps they freeze up. So we'll start with something very simple. Main. Alright, so let's make sure we are all saying this works. Right, so everything works. Oh yeah, okay. Font size, yes. Let me this probably too much. Yeah, good. So this font size, so we'll probably run it from here. So let me get it. I should probably not have this window this big. How do I? So this way you can see what's going on. Go, and then you have hello world. That means that everything's working, everything is same. Okay. Now, how do you interact with Kubernetes? Very easy. They have packages. So this is how you import packages, just like how you do with C# or with Java. You basically include them. So the best part about it is in C# you probably need a reference to an assembly. In Java you probably need to put it in Maven that you need a jar or something like that. In Go, you just refer to a repository. As long as it's a Git repository, it'll figure out how to get it actually, which is amazing. So there's this package called client Go that I'm going to use, and to connect to this thing, there's this client CMD. Don't ask me how I know all these things. It's because I've done this a lot of times. So you'll figure it out. So build config from flags. There's no master URL, it's basically the same. And I basically want to read from my kubectl. So when I say kubectl do all these kind of things, kubectl basically reads this file called config. And it basically says, okay, which is the server you're connecting to, which is the user that's connecting to a big client secret token. Oops, I leave my client secret token, but it doesn't matter. Right, so the idea is that you have all these reference to these things here. And that's how it knows how to connect actually, and that's how it knows it needs to connect to Minikube and things like that. So that's what we're going to use. We're going to basically pass a reference to this file to this thing to say whatever kubectl is using for connecting to Kubernetes, I want to use the same thing actually. So let me get the OS package as well, so that I can create environment variables. Home, and since I don't care about Windows, if I have to care about Windows, I probably have to use the file path library and things like that, but I don't have to. So, and this will give me config and error. So if there's an error reading the configuration in terms of the file is not there, whatever, give me an error here. And and this is an amazing thing about Golang, which sometimes leads to an ISO, is that there are no exceptions in Golang. They're just errors, and errors are values that you basically have to deal with it, right? And it says if you don't have a config, what are we supposed to do? We're going to panic and just give up. I don't care, right? So if it's a production application, you probably want to have a log, or you want to notify your error handler or whatever, things like that. So then there's also this other package that I'm going to use, Go, and it's called Kubernetes. So very helpfully named. And I'm saying new for config, and I'm just going to give the config. And this is going to give me a client set actually. So I'm going to call it CS for client set because the screen state is slow. So usually I have big variable names, but since it's here, I'm going to use smaller variable names, and I'll get rid of this. And if error is not equal to nil, panic error. So, I mean, there are some languages where you look at some pieces of code and then you know this is this language. And if error not equal to nil is like a clear giveaway that you're writing in Go, actually. So now CS dot. Oh, I forgot to give. Uh, it's good. It just says that client side is not used. So unlike other languages, if you don't use a variable, it's a compiler error in Go, which is also one other thing that I really like about Go. So Codebian, pods. Basically, I want to get pods from say the default namespace. Default namespace is what we are looking at. If you pass an empty string, it basically gives you from all namespaces. Maybe we'll do this actually, and then let's do a list. And here it says that I need to pass it list option, so let me get that package as well. Um, just to make it happy. I mean, right now I'm basically saying that I don't really care, give me all those pods. Now, what this is going to give me is basically going to give me a list of all the pods and an error. So, and I can say for pod list dot items. So I'm basically doing a for loop on this, and I'm going to just print out just the pod name and which namespace it is in, because I've got stuff from all the namespaces, so I'm going to do that. As you said, it's a C-type language, as you can clearly see. Dot name. It's wrong here. I did use that. Both of this should be there, so let me find out what's wrong here. Oh, this is should be a method. I need to iterate over that. So yes, okay. So this is good. So if we run this, we should basically get a list of all the pods. So let's see how this works. Go run main.go, and it's going to connect to a Kubernetes instance and all these things. It's going to give us back a list of all these pods that are running. So essentially this works, right? So in a sense, it says some of them are in kube system, some of them are in this thing, but it basically says, and some of them are in Vagmi namespace. So we're good. Okay, so let's do something a bit more interesting. I think, battery ran out. Hello. Oh yeah, I'm back. So now let's do something a little more interesting. What we're going to do is we're going to create the Nginx part. Like whatever we did with Nginx, we're basically going to do the same thing with code and see how that works. So I'm going to have create Nginx method. Right, and I'm going to basically get whatever type that this gives, right? So for example, this core v1 pods, so it gives me this pod interface. So I'm going to basically get this pod interface. To know which pod interface it is, I'm basically going to go and find out which namespace it is in. I think it's in, yeah, it says it's low. Am I still audible here? Yeah, okay.
Maybe can you come front if you...
In case,
Yeah, in case.
I'll shout otherwise, so.
Sorry.
You have another? So this so am I audible now? Good. Okay, so I'm sorry if it's boring, but yeah. So here, basically, I want a reference to this guy, and whatever pod interfaces, I want to pass this in so that it will create the pod this thing for me. Um, so, or what I can do is I can also do, or I can basically have have this return this. So let's do that. Um,
You are looking to namespaces.
I'm sorry.
Are you looking to namespaces?
No, I'm basically getting pods from all the namespaces. So because I did not put a filter on this. So if I put a filter on this, then it's going to give me only pods from the default namespace. So here, if you look at it, it got me from all the namespaces here. So if I run this, it's only going to get me stuff from the default namespace around that. And this is probably the same output you will get from pods, right? So essentially that's it. And you would have all the statuses. I mean, since it's an object, you would basically get access to pretty much all of those things. So let me also get code one. It's actually just, and so instead of having this, so let me say func. Um, so I'm going to return a pod object from this. So the reason I want to show this is that now you are in Golang. That means that you have full access to whatever Go functionality is there and so on and so forth. And these are just objects that are being passed in and returned. So like how you do kubectl, those command line things and all that. I mean, if you have to do anything complicated, you have to do that YAML file. So I find dealing with it in code is so much easier than dealing with YAML files actually. So
Shouldn't you, like, if you do this, implement the same thing for every project differently?
not so in a sense what I suppose would happen is that every organization would basically come up with a standard set of practices on how to do things and so on and so forth. So they will write it may not be for deployments and other things. Say for example now your deployment depends on a config map for doing the configuration, and every time the configuration changes you want to do something special on the deployment, right? Either you do a rolling restart. Sometimes your rolling restart may not be required, but you want to run some commands on it indicating that thing has loaded, changed, or whatever. So for those kind of aspects, I think you write this sort of code to figure out, okay, what has changed? Let me do these things and all that. So we'll do that. So and we'll do this. We'll say name is Nginx, and we'll also set labels such that so what I'm going to do is I'm basically going to say, okay, I'm running Nginx on this. I can say app Nginx, whatever, but I'm just going to choose run Nginx, and I'm also going to set up a spec. And the best part about this is if you write YAML, you don't know whether you're doing it right or wrong because you don't have any type information and all that. But when you're doing this, you also have type information, so you know you cannot go wrong actually. So, because your code wouldn't compile if your spec is wrong actually. And then let's say it's an array of container ports. There's something down there. And we need to have one object container port, and here you can say container port is 80 and name is web or something like that, so that you can refer to this port also. And you can also set a container name here, and you can say message. The thing is that you can actually have multiple containers in a given pod, and they will all share the same IP address. So let me put commas everywhere because Golang will complain about this. Okay, and that's it. So this basically returns. I've basically written a method which returns whatever the core object specification is for pod. I've basically written that. And what I'm going to do here is, after I create this, I'm going to say cs.core p1 pods. I'm going to do it in the default namespace, and I'm going to create my pod, which is going to be the Nginx pod function that I created. Now this is going to give me the pod definition, and I'm going to create a pod. So I'm going to say pod and error. If error is not equal to nil, I'm going to panic on this. I don't need to panic because I can actually check what the error is and so on and so forth, but for the sake of the demonstration and to keep this short, I'll currently panic on this, and I'm going to and I'm going to do this. And I have the p variable, probably I can use this. Just to make sure, do it the same. Right. So now that I have this, so let's try to run this and find out if it does that. So I can say go run main.go. So just to make sure we don't have the kubectl pod here, let me delete the Nginx deployment. And the deployment as well. So now if you see Nginx is terminating, and in a few minutes this will be gone essentially. Yeah, so Nginx is gone, so let's just run ours to see what happens. So what I'm going to do is I'm going to also split the window so that and I'm going to run this in a loop. So every second, basically, this is going to keep refreshing. See what's happening here. So it's first going to list the pods, and then it's going to. So now immediately you see container creating, and it started running actually. So and basically now the fun part about this approach is that now this is essentially what Kubernetes community wanted you to use Kubernetes as, in a sense, as a programmable platform instead of doing this. But essentially, it's the same thing. Now you can expose this with a service, do whatever it is. So one other thing that really helps in development use cases is port forwarding. So you can say port forward, and you can say which pod you want to do and which port you want to forward actually. So you can say, I want to port forward pod Nginx, and I want to say, I want to do the pod 80 to 8080, right? So 8080 to 80. So whatever the pod is running on 8080, I want to put this on 8080, and I will be able to run localhost 8080, and it tells me, I mean, I can access that one. Make sure that I can access it. So not only can you do the service and then expose it with the node mode and all that, you can, when you are developing and then you have a pod and then you want to quickly access it from your dev machine, you can port forward the pod or the service in both cases actually. So that's pretty much what I had for the demo, but I would like to talk about some of the other things that are interesting go forward, because I see since there isn't a lot of already exposure to Kubernetes and this thing, some of this may probably have gone over your heads. But usually they have two patterns in Kubernetes. One pattern that I talked about was like controllers, where you say you have like your deployments, and each one basically needs to say what it needs to do with it. And so you have these controllers. Say for example, you have config maps, and if the configuration changes, you need to restart something, right? So when you're writing software for that, they are called controllers. But then you can have your completely different type. Say for example, now you are basically creating a alert service or something like that, and you want to configure the alert service with various alerts. So you can have your own object called alert that other applications can create to use your base infrastructure or your framework tool, and they are called CRDs, or custom resource definitions, and they are something called as operators. So you will write operators. So whatever a human does to say, okay, you need to, when a new software comes in, go change this file, add this thing in there, and so on and so forth. So that's like a manual set of steps that you do. You can basically automate this whole thing with Kubernetes, and they are called operators. So both controllers and operators use very similar, like the client Go, and they use the watcher and informer factories and things like that, whatever that we saw now, or whatever client Go provides. But these are kind of like new Kubernetes specific tooling that is coming around. Actually, there are a lot of software. In fact, we are building a product which primarily is writing controllers and operators around this to actually ease the DevOps workflow. And then if you're interested in this, you should look at KubeBuilder and Operator Framework. There are two open source libraries. KubeBuilder is by the core Kubernetes team itself, while Operator Framework was created by CoreOS, and CoreOS is the guys who are behind the etcd database. So they have been acquired by Red Hat now. So they have open source Operator Framework, and there are several others, but these two are kind of prominent in the community. And then you can start writing Kubernetes native apps. So what I mean by Kubernetes native apps is that right now you are writing applications assuming, and after which you are containerizing and you're figuring out how to write on Kubernetes. You can actually assume Kubernetes is there, so that, for example, then what it means is that you won't have to read configurations from an environment variable. Rather, you can directly access the configuration map using Kubernetes API to do whatever it needs to. That way, you don't have to worry about, oh, what if this changes, should I restart it, or so on and so forth, right? You have access to the configuration map. If the configuration value changes, then you are notified directly, and then your application, you can write application logic basically to assume that you have all these services and a service mesh and all these things in place, right? Which gives you a lot of power, because we have been writing software in a way where it's running on one particular node or one particular machine. We take a VM for granted and we say, oh, the configuration for it is coming through environment variables and things like that. We are not writing a reactive truly microservices oriented application. But by looking at Kubernetes and you are assuming Kubernetes is there, you can write applications which take care of the service, which take advantage of the service mesh, which take advantage of the configuration maps, which take advantage of secret storage and things like that, right? All that would actually make your code a little more responsive, and you don't have to jump through so many hoops to Kubernetize the application when you can assume that it's going to be deployed on Kubernetes. And there are all these, there is DevOps and there is SRE actually, right? So there's this thing called site reliability engineering, which basically deals with, say, what happens when there is an incident, or how to avoid incidents that can happen to you, this thing, right? So so what happens is basically what we have all been doing, in a sense. Look at log files, get notified of errors, and then deal with it at a later point in time, right? And after the incident has happened, we know how to go about and fix it, and we have been optimizing on how to proactively address those things by getting notified rather than customer telling us about it, right? We have been good at this. Now with monitoring, it takes it even a way forward. Say for example, even before there is a problem, that say for example, you're sending out a lot of emails, but there is some provider that you're using, he is having a downtime actually, right? And because of which he is not completely down, but his rates of sending these SMSs messages have gone down drastically. So what
you used to send 5,000 messages normally, but now you're only sending 500 messages a minute, right? That means that if you are monitoring these as gauges and you can find out these are running, and then you can set alerts saying that, oh, if it drops below 80% of this thing, alert me when you're doing this. So that is even more proactive, right? It is not on the incident of an error, but even if the operating limits of the applications, once you have identified what the operating limits are, and you can basically configure it to say that, okay, if it's behaving abnormally, immediately tell me. Or if there is a huge spike in traffic, maybe somebody targeted a botnet at you and then you're drowning in traffic and you don't even know it because you're behind a CDN, and you will only know about it when the CDN basically stops rejecting traffic, or they say they do a pass-through, right? They're not protecting you anymore. Then if you get to know about it, it's really bad, right? But instead, if you have monitoring mechanisms and you say, oh, there is an unexpected spike in traffic, maybe we should do these things, right? All those kind of things, monitoring actually helps, actually. And even data storage is becoming, kind of, it's changing. I mean, you have one talk on Cosmos DB, which is very interesting because that's kind of a cloud native storage where you don't have to worry about, oh, which machine is this data sitting on, right? You have a service and then you access the service and it can scale other. And there are also open source variants. So Cosmos is essentially hosted on Azure, and you're basically, so this is one of the most difficult things for me to digest is that, yes, you're using the service is awesome, but we have been burnt many times trusting data to somebody else, right? Running on Azure as a compute platform is a different thing because it's commodity, you can always switch over at some point in time. But if you are tying your core to something like Cosmos DB or DynamoDB or something like that, it's very difficult to move your app out. I mean, even though they say we follow Gremlin API, we follow MongoDB API, so if you want to move out, you can always basically you write for MongoDB API spec and then like instead of using MongoDB, use Cosmos DB, right? That sort of thing. But once you've used Cosmos DB, you can't go back. Right? It's easy to move into Cosmos DB, but it's very hard to move out of Cosmos DB actually. So to that effect, there are open source databases like CockroachDB, which actually provides PostgreSQL compatibility. It's open source, it's Apache licensed, you can install anywhere, and it scales, it transparently does load balancing for SQL on your this thing. And it's really interesting. It follows the Google's panel paper that they wrote to actually have scalable SQL data storage this thing without having to deal with the sort of like a master slave sort of thing and all that. So here these are just nodes in this thing, and they can tolerate failure and they can get back up and they can synchronize among themselves. And similarly, there is also this open source project called Vitess, also by YouTube guys. They did the similar thing for MySQL, where it acts as a layer on top and provides horizontal scalability for SQL in an amazing way. And then once you have figured out how service meshes work, you can use Istio and things like that, where you can do like A/B testing. So you are rolling out a new version of service, and you say 20% of traffic, let's push this to the new service. So you can do it at the top level with DNS and things like that. With Istio, you can do it at the microservice level. So you can say this version of microservice is new, so route 20% of traffic to this microservice and to do all this thing. And they have very complicated routing logics that you can implement and then do this sort of thing. So I mean, the world on cloud native tools is like amazing. There's a lot of things happening there as well. And finally, this is all just at the open source world, and when the rubber meets the VM, I say, right? When on AWS and all that, things are amazing because now AWS Spot instances, they are priced at 30% the cost of on-demand instances. Actually, right? Most people, when they launch AWS instances, they install on-demand instances, and then in order to cut costs, they move to reserved instances, and which basically saves them about 50%. But your Spot instances are even cheaper. So if you have like a variant load, which most e-commerce sites have, and like almost any of the applications that we see today have fluctuating loads. And for those kind of things, you can have like a core reserved instance provision. And whenever there is Deepavali or like any of these functions, or like Halloween, or like what are we doing, any of those Black Fridays and things like that, then you can use the Spot instances to actually do that. And Kubernetes lets you do that because you clearly know which is a stateful service that you need to store state and which are stateless services, right? You write 2 different deployment descriptors for each one of them. And so you can basically say, you know what, there is no capacity on this, so spin off new instances on Spot instance, have it join the cluster, and all the new stuff will get allocated on this thing. And you can also have like price bidding and things like that, because Amazon gives you like, you bid on a price, and then once it's available on that, you can basically do it. And if it dies, then you switch to on demand. Or if sometimes the spot instance prices go higher than the on demand instances, in which case you can launch on demand, kill the spot instances, and do this. So it opens up a whole deal of possibilities with cost optimizations, which was earlier not possible if you are managing VMs manually, actually. So that's my spiel. And yeah, Vagmi, I'm from Tarka Labs. I mean, and I'm from Sedin. I mean, you know, Jagu has been around, and I mean, a lot of people may have seen him roaming around. So we work together. So, so that's me. And if you have any questions, comments, please let me know. Yeah. Hopefully, I didn't keep you too long. I didn't even. Yeah, I have 30 minutes more to spare. So.
Small bit.
Oh, thanks, Mark.
So in case you are ready, you can get in touch with him offline also.
Yeah, and I'll be here for a while. Yeah.
Yeah, you can get in touch with him offline. So tomorrow we are having an architecture session, architecture session on. We are going to